For those people that I'll just do a quick overview on what the Core One is all about. Core stands for CISC on Risk Engine. Where we're at right, and the Risk Engine is fourth. So CISC, we really haven't started working on that piece. What we're going to do is we're going to build an interactive fourth-based language that has arrays and has all kinds of high-level processing, high-level commands or syntax that people can, easily create, build their applications in. So Dimitri has just got the compiler integrated in with the interpreter, and it's all working. I'm gonna do a short video on that in just a second. You can put the risk on a fourth computer, which a fourth computer is different than the Core One. The fourth computer uses the Core One, but it has the outer interpreter and compiler built in, and it's all written in system Verilog, so it's going to compile like insanely fast, as fast as you can feed it data over the serial line, which could be SVI. It could be much faster, than RS-232. So like I said, fourth is a risk engine. We're using very high level system Verilog code, which what it means is we can parameterize, like, for example, the data width, how large the address buses are. You change it from 32-bit to 16-bit to 48-bit to 128 bits, and you resynthesize, and now you have a computer that's a 128-bit computer, depending on your application, how wide you need. If you're doing embedded systems, you may only need 16 bits. Most embedded systems, 16 bits is more than enough. So now a Core One, so a fourth computer, sits on top of a Core One. In the FPGA, you have block RAM, and you have a pretty good amount of high-speed SRAM that actually can operate at the speed of silicon. And this typically a propagation delay in an FPGA is about 2 nanoseconds. So you have 2 nanosecond SRAM built inside, and you can, if you have 10 cores inside, you can have basically divide the total amount of RAM bits inside by 10 and assign them to each core, so they all have their dedicated SRAM. You also have ROM inside of an FPGA, so you can actually write programs, and like a bootloader, inside the FPGA, and when the Core One boots up, it can immediately start executing CFAs. It can fourth code. So for $20, you can have a 10-core system with the fourth computer very easily, maybe 15 Core Ones. Yeah, and so one of the other big things is you can create your own opcodes, and this is really important. So Brett has an application where he's going to be, creating code that calculates a mathematical equation. So what you can do is you can kind of factor out that equation into maybe 5 or 6 different functions, and you create opcodes for each one of those, and you write system Verilog code, not fourth code, but system Verilog code, so it runs the speed of silicon. And now you can go ahead and call those words. You can write that mathematical expression in high-level fourth, but it's calling these opcodes that are running at the speed of silicon. So that's a big feature I think for people that are doing these sorts of things, like they want to emulate or virtualize a quantum computer kind of thing, we want to steal and borrow high-level concepts from other languages that we really like. You know, struct in C is a nice feature, and of course you can do that with create does and forth. But we probably would emulate something like struct, you know, build it and have it available as a high-level part of our language as we build on top of this core one. You can, and of course, you can network these things together. In multitasking, I absolutely hate time slice multitasking. I think it's just stupid. You know, you're either allocating too much time and the processor is not doing anything, or you haven't allocated enough time, and now there's some function in your code that can't quite get done. It's crazy. So I developed this triune multitasking model where basically you have it's a foreground, background type processing. I use a counter timer to do this. And then you have like a task list, and you basically put forth CFAs in this list, and you do a fetch execute until you're done. And you, but with the core one, you could easily write where you would use multitasking on a regular CPU. You would just simply make a dedicated process written in system Verilog using an always statement, and you would have parallel processing instead of multitasking. And that's so a core one based system would be incredibly real time. I mean, you could operate at 10 megahertz and not miss a beat, and have 100 processes being executed at one time. If you want to get started cheaply, the Arduino 3.1 is low cost lattice FPGA. The FPGA costs $5, and we're using this as a development board. So everything that you've seen us develop has been on this this inexpensive board, and we pretty much finished the hard part of developing the fourth engine. Like I said, we now have the compiler working and integrated with the outer interpreter, and Dimitri is adding some words like for next and do loops and other things, basic things that we use in fourth. This is the chip I'm using on my AI Playground Core 1 development board. Is this LFE UM585. I'm using actually the 25F, which is 25,000 LUTs. But you can get up in the same BGA package, you can get up to 85,000 LUTs. And the 85,000 LUT chip is only $45. But I bought one of these boards, and they're out of stock now. But you could also, if you wanted to do something like a large project, you could use this board. You could actually use, because we did everything in System Verilog and source code, it basically should run on Xilinx, on Microsemi, on Altera, on any FPGA. So it should, whatever your favorite FPGA is, it should run on it. So the AI Playground development board, we put an ESP32 Wi-Fi Bluetooth computer on it. So we'll run Brad's eForth on it. And this is so we can access, things like your phone and the internet. I don't want to have to screw around with talking to the internet when I can just put a $3 part on the board. And Brad and many of the other people using eForth have written a lot of code to do internet stuff. So the internet comes free. it's using the powerful, like I said, this FPGA that can go up to 85,000 LUTs. To give you an example, you could put 50 core one, 32-bit wide core ones with dedicated memory on a $45 part. I don't know what on earth you would use all that processing for, but you could do it if you wanted to. All we'd have to do is run boards with the 85K part because it's pin for pin compatible. The board also supports Arduino Shield footprint, connectors. So all of those Arduino Shields out there, you can pop it on the board, and like the one fellow is doing the music stuff. There is a music shield, an audio shield for $20, and you want to do mute, and it's got high end, has DACs and stuff on it, and audio amplifiers, and you can plug it in there, and you could start playing around with the Core One, playing music, for example. Or it's good.
I have a little question.
Yeah.
The Arduino Shield support, is it 5 volt or 3.3 volt logic?
Well, that's I'm glad you brought that up. From what I was reading, because I haven't done a lot of stuff with the shields, 3.3 volts would be good, because 3.3 volts is easy for me. If I have to go with 5 volts, then I may be able to do that because you can set FPGA banks to be a certain voltage. Do you think we can get by with only 3.3 volt system?
The reason why I bring that up is that a lot of the classic Arduino Uno shields are 5 volts because the AVR processor used by the original Arduino Uno has 5 volt logic. But since then, much of the rest of the world is, as you know, has moved out to 3.3 volt or even 1.8 volt. So if you plan on gaining support for a lot of the old Arduino Uno shields, you'll need 5 volts.
Yeah,
if you want compatibility with anything made more recently that isn't marketed specifically to Arduino, you probably want 3.3 volts or even optional 3.3 volt / 1.8 volt. Like, for instance, this isn't a shield, but SD cards, for instance, are natively have 2 modes, either 3.3 volt or 1.8 volt. And to use an SD card with a SDHC or SDXC, that is, not the old original SD cards, if you want to use one of them with a 5 volt, you need to use a board that converts the voltages for you. So that's one thing to take into consideration one way or another before you commit to a particular design and then realize that, hey, wait a minute, either you want to use these Arduino shields that are 5 volts, or you want to be compatible with everything else in the world that runs 3.3 volt or 1.8 volt.
Yeah, so my thinking is I would rather make it a requirement that you have to buy the 3.3 volt version. I'm not, I'm looking at moving forward, not backwards. So yeah. I could be able to add the 1.8 volt. So let me thank you for that input. I will look at making, like assigning the bank, or I could maybe with the jumper, you could change it from 3.3 to 1.8, or just bring the 1.8 out to a pin. Okay, so moving along, not only do we have the Arduino Shield connectors, we also have 100 extra FPGA pins. This FPGA monster, from the standpoint of pins, it's a 381, and it's a BGA. And it's always so much fun. Somebody needs to mute. So we have 100 extra FPGA pins on two 50-pin headers that come down on the board, so on the back side of the board. And that's going to be custom boards. Like I'm going to design a whisker. I call that a daughter card. And I'm going to design a whiskers board for the bottom. And then we can snap this on top and build really intelligent mobile robots. The other thing is that on FPGAs, we have an incredibly high-speed serial interface called SerDes that can go up to 2 or 3 gigabits per second. And what I did was I hooked 2 of those ports to standard micro USB connectors. So you could use USB jumper cables and you could actually network the boards together. I'm not sure why you would need to do that, but it was, it just cost some traces and a couple of connectors. So I added that. We're going to support a 4.5-inch color LCD screen on the first board. I want to go to a full screen to support later on, but yeah, there's already so much on this board. We're just going to support like an SVI, maybe even what's the other direct mode that has individual pins. But anyway, so we'll support a 4.5-inch color.
I2C?
I2C.
No, it's not I2C. It's kind of like the RGB. It's these little 4.5-inch boards have they called it a digital interface or something, and it basically you just put IO lines up to it.
One
and it's supposed to be faster. But it'll probably just be SPI or I2C. The other thing I have on this board, which is quite interesting, I misspelled main. That's fun. I have a 64,000 by 32-bit wide cache SRAM that you can access in 4 nanoseconds. So this chip was designed to be cache memory on motherboards. And that's going to be our main memory for the 4th computer. So, it's almost not quite as fast as the FPGA, but it's damn close. So we can probably see the 4th computer running up over 200 megahertz. 200 million, let me rephrase that, 200 million 4th instructions per second. For the simpler instructions. Remember, we can make complex instructions too, so that take multiple clock cycles. But if we have things like dupe and drop and swap and all that stuff, that's going to be 1 cycle. So that'll be 200 FIPS. And another interesting thing on the board is we have 2 gigabit of 16-bit wide parallel flash memory. And it's a 45 nanosecond access time. Also, I put an SD card to use as a hard drive on the board. Now, I'm going to talk a little bit more about that flash memory in a minute. This is the board in its current state. You'll see that the FPGA, I got it all routed to these connectors, and so I just finished the FPGA. That took over a week. But the rest of the board is going to go by pretty quick. So I'm expecting probably by the end of next week, I'll be able to send it out, but it's within 2 weeks for sure. It's only 4 inches by 2.8 inches. So here's a 3D view of the board. Now the 50-pin connector, which is right inside of the Arduino connector, is shown, and it should be populated at the bottom of the board. This is the top side of the board. Over on the right, you see the footprint for the ESP32. The flash and the RAM are in the middle of the board. Those footprints. Here's the top view of the board. Here's bottom view of the board. I have parts on both sides of the board. So let's talk about architectures a little bit. So the Core 1 fourth computer, which means it's got the interpreter and the compiler built into it. So it's a full fourth computer. We're using that $5 FPGA. I talked about the Arduino board. So you can, this is a block diagram of what you would have in it. So you have the serial port UART, which we wrote in source code. We're not using an IP block. The outer interpreter compiler, and then that sits on top of a Core 1, which is the execution engine. It's basically like you know, like a Shaboom or something like that. It's equivalent to that. You have the FPGA boot ROM inside the FPGA, and you have the FPGA block SRAM, which is using SRAM inside the FPGA, and we're getting 3 or 4K of 32-bit wide, which is a lot of SRAM for a fourth. You know, typically fourth is, you can have almost all your fourth program in boot ROM. You don't need a lot of SRAM to run a fourth program, typically. So you could actually put all of your source code, or I mean all of your fourth code, in the boot ROM, or you could copy it into SRAM, either one. So this is a $5 part, and you still have, so this part is 5,900 LUTs, and we're using 3,500. So you have 2,400 LUTs available. You could write a lot of system Verilog code in 2,000 LUTs, a lot. So you could do a lot with this little $5 FPGA with this, and it's basically a fourth process, $5 high-speed fourth processor that's running. It could run up to 200 FIPS. This is an example of possibly building like a robot or something using just the $5 chip. So you would have the fourth computer, and it sits on top of these system Verilog processes that are running motors, sensors, GPS, wireless, anything you want. So there's a high-speed fourth processor for $5. This is the development board. This is kind of what we're doing inside, what I'm thinking about. And you know, as we go along, we may find that we don't even need a Core 1, but this is an idea how you can assign cores to do the different tasks. So you have the fourth computer that interfaces with the user, has the compiler and the interpreter built in. It's got the 64K cells of high-speed SRAM hooked to it. You could have, for example, a Core 1 assigned to the flash, a second Core 1 assigned to the SD card, and a third Core 1 assigned to the display. And you would use memory mapped shared registers for the fourth computer to send information and receive information from each Core 1. So let's just say that you have a database on the SD card. The fourth computer could tell this Core 1 to go search in the database for some data. Maybe it takes 20 seconds to a minute. So this Core 1's running in parallel while this fourth computer continues on and just waits until this Core 1 finds the information and then flags the fourth computer that it found the information, and then it could transfer it over to the fourth computer. This Core 1 could be doing graphics and stuff, you know, different shapes and things. So the fourth computer say, you know, display a square of this dimension on LCD display, and then it runs off and continues processing. And this Core 1 in parallel will put that square on the screen. Or maybe the fourth computer might say, load an image from the SD card to this Core 1, which we would put a little bridge in here so that these two guys could talk to each other and not bother the fourth computer. Now, the 2 gigabit of flash is interesting. We have 64K by 36 bits. So 64,000 cells of SRAM, right? And we have this extra long-term memory flash that can actually hold 1,000 of snapshots of SRAM. So think about this. You, instead of loading programs, you load in a snapshot. So you're doing some sort of processing. And by the way, you can load a snapshot in probably less than 1/10 of a second. It might even be less than a second, but it's definitely less than 1/10 of a second if the snapshot was the full size of the SRAM. So you could have all of these snapshots saved out in flash. The flash is about 45 nanosecond access time. So it's 1/10 the speed of the SRAM. So you could maybe, like, let's just say you had a word processor. You might have a snapshot that's a word processor. You just load it in and you got the environment the way you left it last time. How about that? With all the RAM variables and everything, will be there, the way you left it. You want to do a database programming, you load the database snapshot. You want to do, I don't know, something else. You could have up to 1,000 snapshots into this flash memory. Well, we could also partition this flash memory not to just hold snapshots, but it could hold a lot of things. It could hold source code, forth source code. It could hold compiled source code, right? CFA compiled source code, and loaded in, and then and maybe in that with that. So it could hold compiled words, right? Colon, to semicolon. It could hold that whole thing into flash. So we're trying to think outside the box here, how to maximize the features of this Core 1 project. So this is something that I've thought of since the last time I gave a presentation about these snapshots. So why don't you guys think about that and let me know what you think. Or how can we utilize the flash? We have long-term storage, obviously, in the SD card also, but the flash is going to be way faster than the SD card. So we have this long-term memory. How can we utilize it in a fourth computer? But it's going to be there. So, the last thing I want to do is show Dimitri's video. Where is it? If I can find it. So you're all welcome to join this. We started a Facebook page called AM Robotics. We have a few people. We have several people in Silicon Valley FIG and others kind of using this as a place to talk. So here it is right here. So there's a little Arduino board, and he's typing in red, executing. You see the LED is turning red, blue. So that's showing.
We don't see your video.
You don't see the video?
We see your face.
Really? Hang on a second.
Did you share your screen?
I was in the share mode. I didn't change it.
No, you're not in share mode.
Okay.
You're showing your screen, your face.
All right, let me try it again. Oh, shit.
Now we see click to enter presentation in your upper left.
Yeah, I know. Oh, okay. Let's see. We're sharing, right?
Yes.
We see your PowerPoint. Now we see, I have tried port. Now we see a couple monitors and a little breadboard.
Okay, that's it. So, yeah, this is Dimitri's latest demo. So here he's typing in, showing the outer interpreter working. And you can see that he's working on the, turning on the LEDs. There he typed in yellow. Now he's going to do a fourth definition. So he's going to define, because yellow didn't work. So he just defined yellow. And now he's going to type in yellow. So that shows the compiler working. So that's my presentation for the day. Where am I? Get back. I always love having all these screens open. Pause share. Okay. I stopped sharing, right?
We still see your Facebook page and stuff. So as far as I can tell, you're still sharing.
Oh, here it is. Okay, there we go.
There we go. All right, you are not sharing at this time. We see your face.
So there's still time to make some changes on the hardware, although you'd have to do a little convincing to get me to change it because I want to get it done. But if you have any suggestions, I'm like to hear about it. If you have any comments on where we're going with this project, you think it's going to help us promote forth, I'm committed to do the project no matter what. But any thoughts?
Voltages, I would suggest doing 3.3 volt versus 1.8 volt in software. Like I know on the RP2040, there's bits in a register that you can use to control a voltage. So you don't have to hardwire it with a jumper or anything.
Okay. Anybody else got any comments on it? By the way, I am going to be sending some of these boards out to SVFIG because you guys bought some Listers boards. I haven't delivered them yet, so you're going to get these. Probably be more fun.
I have a few comments.
Okay.
So, Crystal Losinski here. I think you made the right point about lots of little processors being the place to go. I think it's sort of very difficult for a single fourth processor to compete against like a RISC-V chip or something like that. But if you can get 50 processors in a board, suddenly that gets very, very interesting for numerical applications. And the problem is, say you're doing a numerical application, the computers aren't doing it. You want your own little supercomputer. You pull in an FPGA board. It's really difficult to write software for FPGAs. I'm a hardcore Python programmer. I just started a master's degree, and my concepts about what Verilog programming was, I was completely wrong. And fortunately, I didn't start doing it myself. I would have run into every mistake in the book. But give me a network of 50 fourth CPUs, man, I know how to program 54th CPUs. Okay, so that's one. I think that's the real core target market is because in your previous talk, you said that a single, I forget the exact numbers. In fact, I wanted to ask you about this. You said a single RISC-V chip took 10 times, if I recall correctly, 10 times as many LUTs as one of your fourth CPUs, right? So that begs two other questions. One, is the frequency as high? Maybe it's lower. And two, if I have 10 of these, or say 5 of these, are they faster for doing some kind of parallel operation than a single one? I suspect the answer is yes. I think there's a really good paper to be written here. But I think if you chase that corner of the market, because the average person doesn't care about, good software. They don't know shit about good software. What they do care about is you know, I can get this much performance. You can do this many calculations here. So that's one target area. And the other target area, which I don't think you talked about, well, you talked a little bit about real-time control, right? And I'm sure you know about the propeller chip, which has 8 CPUs that run forth, but they have tiny amounts of memories, right? So another interesting place is sort of the 8 CPUs that all connect to the outside world, which also talks about digital to analog, which I don't think I heard mentioned on your board. So I think those are the 2 target markets you should be focused on. And, you know, certainly the one that's pulling me into this whole thing is the high performance one. But anyhow, that's my comments. Okay, so let me just make sure that I left the questions here. I'll ask you to read.
I appreciate your comments.
I'd like to ask you the questions again. So how many, you talked about this briefly. How big is your chip compared to the RISC-V chip? That's the first question. And what's the frequency that you can run those 2 chips at? And if you did a benchmark, how fast would they run on 5 of yours versus how fast would it run on one of the others? Sort of that whole series of questions. Thank you.
Okay, so yeah, I might have been wrong on the size of the RISC chip. Someone told me that they saw a stripped down RISC core that was about the size of ours. But the difference between the RISC-V and ours is our instructions are much higher level, right? It's a RISC.
I totally agree.
It's really simple instructions, right? It's move T register into memory location. You know, ours is all forth words, and they're operating at in 1 clock cycle on most of the primitive boards. So I would expect if you could writing forth on our system would probably be much faster than the RISC as far as the number of instructions not instructions, but if you write an equation on our system, and let's just say you just write it in forth, which isn't the fastest way to do it. System Verilog's the fastest way. But you just write it in forth versus something written in C running on a RISC, I would expect it to run faster. We will do benchmarks when we get these boards out there. You know, please, you guys need to help out with this. It can't just be Dimitri and me. This has got to be a group effort. You guys got to get on this. But you can do things like that. You know, I'm expecting these boards, they're not cheap. I want to throw in $20 for that I'm going to split with Dimitri. They're probably going to cost about $100 a board when we first get them, because we're making low volumes, low quantities, and we'll put the 25 KLET chip on there for that price. If you want an 85 KLET chip, which is 4 times the amount of LUTs, we could put 40 to 50 of these core ones on there. I'm interested in running that anyway. If I had a few people buying them, it would be even a greater incentive. I don't have to make any changes to the board. All I have to do is change one line in the BOM saying to use the 85 KLET chip instead of the 25. They're pin for pin, and we could get those. And remember, the boards are networkable over the high-speed SerDes. So you could get real short micro USB cables and plug these guys in. You plug 10 boards in, and now you have 500 computers. You can make your supercomputer at home, you know, for less than $1,000. Well, if you're starting to buy in quantity, you can get the price down. For less than $1,000, you could have 500 32-bit cores working on a problem.
Well, when I see the application of this being is really low latency applications, because
absolutely,
because let's say you want something that you want to be running in real time at very low latencies, just add another core and have it run that core devoted specifically to what you're doing. Whereas with what I'm doing with Zepto for, I'm limited by the fact that I've got only 2 cores and I have to share each core amongst any number of tasks, which is limited to how fast I can context switch, which I can context switch faster, but that means that the overhead of the act of context switching becomes greater. Whereas with this, if you just say, I'm going to create another core on my FPGA and I'm going to have it run such and such all the time, you've got very low latency.
Processing. Hmm? Yeah, and you could also see, let's just say that you're doing PDM on a motor. I would just write that in System Verilog. I wouldn't put a Core 1 on it. I would create for every pin. Let's say you have 10 motors. I'd have 10 System Verilog, always statements that are managing each one. They wouldn't use that many LUTs. A PWM is probably 50 LUTs or something, and times 10 motors, that's 500 LUTs. You have plenty of space. So if you want absolutely zero latency, I mean like 200 megahertz operation, you write it in System Verilog. So, but you don't have to. If you want to save your LUTs, write it in Forth. And then you look at the places in your Forth program. So you'd probably write your whole program in Forth and say, you know what, I have a latency problem here in my code. So I'm gonna take that piece of Forth code. I'm gonna convert it to System Verilog. I'm gonna assign an opcode to it, and now it becomes a fourth word in the dictionary, and you just call it, right?
Yes.
So you're 100% right. This would be the most awesome real-time, system for embedded machines, that's what I am, right? I'm a roboticist, and that's what I'm looking at.
Because I think throughput is less important than latency, because if you want throughput, you can use a modern x86-64 or ARM64 chip in a big system. It'll give you all the throughput you want, but it'll give you terrible latency.
Yep. Yeah, you're 100% right. I mean, FPGAs are, it's funny. I've been using them for 20 years now. I'm not going to tell you I am an expert, because I wasn't specifically using them for 20 years. But throughout the years, I saw so many engineers out of school saying, I'd ask them about, have you ever thought about using an FPGA instead of a micro? Well, I took a course in college. It seemed too hard. Really? When I went to Redwire, they never used an FPGA, not one time. They had when I got there, I was the 44th employee. They were 10 years old, building space hardware for the ISS, never once used an FPGA. And I said, please let me put an FPGA on the next board. So I designed a computer board that they're using in for their whole payload section, put an FPGA on it with their 32-bit Arduino processor. I forget the name of it, AV something. And now they're using, I put in that. These guys were Arduino people. Yeah, these guys were Arduinos. I walked in there. Everything's done with an Arduino.
They were putting Arduinos in space?
In space, yeah. And it was all Arduinos. That's all they knew. And so I opened their eyes up to FPGAs, and now it's big over there. They're using FPGAs. All the engineers learned it, and they're using it. So another thing that I think it was Mark was saying, another aspect for this Core 1 development board is it's going to make it so much easier to learn FPGAs, because you don't have to do the test bench, you don't have to do the simulation, unless you got some really crazy timing problem. You would do a simulation, but you can literally create little snippets of system Verilog, make it an opcode, and interactively debug it, right, using Forth.
Don, I have a question about that. Are any of these systems open in the sense that you can directly program the LUTs, or are they all? This is all still you have to go through their tools, and you're stuck with System Verilog as the abstraction. And I think that's the core about why people don't use FPGAs as much, is that the whole ecosystem is closed. Xilinx and all these companies have their secret sauce inside, and they use the tools as a way to, you know, if these were open in the way that a CPU is open, and somebody can write code for it and develop their own open source tooling, like that would be what would unlock it. But the problem is that that's not the incentives that the different makers of FPGAs have. They want it to be, you're locked into my particular tools and my particular set of ecosystem and all of that.
Yeah, I've heard a lot of the same, and that's part of what's put me off to the whole FPGA thing myself. Like with what I've done with Zepto for it, everything is open, down to the instructions, to accessing the peripherals. Everything is open with regard, except for the ESP8285 firmware. It's the only non-open thing about everything I've been doing. Whereas with FPGAs, it's so much like, oh, you have to use our tools that only run on Windows, then all that. Even though I've heard that it's gotten better, and I have a icebreaker sitting in its packaging, which I've yet to open, which I intend on opening at some point and playing around with, but that's another story.
Yeah, so there's do a web search on open source FPGA development tools. There's people that are in the open source community have started working on these tools. I don't know how good they are. One of the things that we made it a requirement to our project is everything is source. So the way that these companies lock you into their FPGAs and their tools is they have this really nice, they call it an IP library. So you want pulse width modulator, you have this schematic, and you drag it in there, and you connect up some wires, and then you can use their pulse width modulation, and you can instantiate as many as you want. Well, it's a black box. They have control over it. You don't know what's in it. So our entire Core 1 project is source. Dimitri even wrote the UART, which you would get out of the catalog typically. But we wanted everything open source so that you could put it on, if you like Altera, you put it on Altera. If you want Microsemi or Xilinx. So, Brad, we're going down that road.
But I guess what I mean, Don, is it's not just that, right there you're stuck at the level of, okay, I can move my System Verilog between the stuff, but I'm still stuck at the abstraction level of System Verilog. If I want to build a Forth that, you know, I can interactively conjure up a bunch of LUTs doing a thing like that, I have to rebuild the whole thing, and I'm back. I'm still a System Verilog developer and not a Forth developer. I'm not able to interactively change the configuration of the LUTs or build out gates in Forth. That's I think the frustration I've had whenever I've looked at one of these is like, okay, I got to fire up this tool chain to compile a thing once, and yeah, if I bake in a particular piece of stuff that I want, then I can have that and Forth combined to it, but I can't do anything dynamic. I can't,
Yeah, that's but like I say, there is I know there's an open source tool chain out there. I don't know how good it is. I don't know if they support which manufacturers they support, because I would think that each one has their own proprietary.
I mean, they literally lock. My understanding is that for most of these architectures, they lock you out. Like you have to have the configuration for the FPGA has to be signed by the tool chain that came from the manufacturer, because they don't want to tell you enough about the internals of the FPGA that you could that's a competitive edge for them. So they want the tools sitting between you and the thing, so they can both. There's an element of locking you into their tools, but there's also an element of hiding from their competitors all of the particulars of their particular system and their routing fabric and all of that.
That sounds like Xilinx.
Yeah, it's Xilinx, right?
Yeah.
Essentially, they don't.
There's a lot of other. Take a look at Lattice, because Lattice is the up and coming. They sell a lot of chips now because they're the low price leader. They have very high performance FPGAs, very low cost. They have a $5 one, which most FPGAs are like 15, 20, for most of the time that I've been using them. They have the first $5 one, and there is an open source. But I think that the advantages of a forced system in System Verilog, I think it's huge. And you're going to be getting one of these when they work. So I'm going to be bugging you about.
Refresh my memory. What's the name of the particular FPGA that you're putting on these? I flubbed that. Keep in my searches here.
Oh yeah, it's a Lattice. Go back to mine.
Because if there's enough information out there to be able to actually reconfigure the LUTs on the fly, that would really be a thing. But I feel like that's the. I mean, for that matter, on phones and desktops, that's one of the challenges is that be so much you could do with a programmable thing like an FPGA, but if you have to cycle all the way back to the compiler, that's the. Anyways,
break.
So it's called the Lattice ICE 40 Ultra Plus 5K.
Could you type that out as a chat?
I'll try. Yeah, let me get back.
That way we'll have a audio YouTube record and also in the chat. I wanted to take this moment. We're teetering on the edge of pulling the plug on the recorder.
Sure.
So I would like to mention a couple of things, and then we can talk at leisure about other stuff. We mentioned earlier the HES-ware cartridges for the, let's see if we can get a good picture, for the Commodore and for the VIC. I have reverse video at my end. I assume it's coming out the right way at yours. I have a few of these. So if you're desperate to have one or two of one or the other or both, drop me a line. I'm fourther@comcast.net. If you are willing to adopt the repository of this and other Forth stuff to dispense them upon request, there's all sorts of stuff that I could send you if you're willing to be the closet of the Forth interest group. No matter how much stuff, how much space you have, I could fill it up with crap, with stuff, old issues of this and that. Probably not complete sets of anything because that would be too easy. I'm throwing old copies of boxes of brand new, unused, just fresh from the publisher, copies of the blue edition of Starting Forth into the recycling bin as mixed paper. So I'm happy to divert it to you. Anybody that's interested in doing that. So if you're interested in having one or two of these, they're available. I'd like to say hi to Andy Korsak, who joined us a little late in the game. Thank you for joining us, Andy. It's good to see you. When are you going to come and talk to us about your direction finding? It's an interesting topic, and we'd be pleased to hear about it.
Oh yeah, hello everybody, and the three of you that I addressed directly because I remember you, but the others I don't know. I think I've seen some of the others off and on when I check on Zoom once in a while. But yeah, so this project is it's taken me years. You know, as I get older, I'm 86 now. I'm just slow, and I make so many mistakes, but I'm enjoying it. Using G-Force on a Raspberry Pi 3B. And now here, I know that Bill Ragsdale also was doing some Doppler direction finding projects. And I'm sure he's going to be interested in seeing what I've got. But I've almost got it ready, but that's what I said for the last 3 years. So I keep working on it. It's enjoyable. But back to you, Kevin.
Okay. You've probably also seen Brad Nelson and Dennis Rufer and Doug Hammond and maybe a couple of others at the Stanford meetings. So there you go.
By the way, this is Doug Hammond. Andy, I want to let you know that I am now a ham radio guy too. I'm a call signer, Whiskey 6, Echo Charlie Mike. Are you still here?
ECM. Yeah. Okay, nice to meet you.
Yes. I look forward to hearing from you.
Okay.
All right. I think it's time. Does anybody else have anything that they want to put on the record before we pull the plug on the recorder? All right. The starting of the recorder is ceremonious. The ending of the recording is unceremonious. So Brad,